Hello, everyone, and welcome to the last episode of this class, talking about separable differential equations that come from real-world situations, solving those using the techniques that we have introduced in the previous couple of episodes. Let's consider the case of what's called exponential population growth. Now, exponential population growth is characterized by a really interesting property. When you say that a population is growing exponentially, what this means is that the rate of change of the population over time is proportional to the population's current size. Let's try first of all to write down a differential equation that corresponds to exponential population growth. I'm going to introduce some notation here. I'm going to let p as a function of t be the population at a time t. And I'm going to try and, in this notation, write down a mathematical statement that is the equivalent of this English statement here that I've bracketed. They say the rate of change of the population. The rate of change of the population. So the derivative of the population is what will tell me its rate of change. They say is proportional to. We remember that proportions mathematically are represented by a constant multiplied by. So I'm going to let that constant be called k. Proportional to the current size of the population, and symbolically the current size of the population would just be represented by the letter p. P here is standing for the population at time t. So this differential equation right here, p prime is equal to some constant times p, is the differential equation that corresponds to exponential population growth. I think that we can solve this differential equation, using the technique that we introduced in episode 3. I think this differential equation is separable. And to verify that, I'm going to go ahead and try and separate the output variable p from the input variable t. If, for example, I pull p over to the left side, and I get 1 over p times p prime, leaving the constant k behind, here is the function on the left that contains no copies of the input variable. And here is the function on the right-hand side that contains no copies of the output variable. And here is that all-important product on the left side. I can integrate both sides with respect to my input variable. And I can convert that integral on the left side to an integral that is in terms of p instead, turning p prime dt into just dp. Okay, now if I integrate 1 over p with respect to p, I get the natural log. And if I integrate a constant, the integral of a constant is just constant times variable. So I get k times my variable t, and then plus c in the back. All that's left is to solve this for p, using, for example, an exponential to get rid of the natural log, and using, for example, a plus minus to get rid of absolute value. So this would be the template of all the functions that satisfy this differential equation. P prime equals some constant times p. Now, this expression, as we've written it down, is kind of complicated. So what I'm going to do now is I'm going to simplify this expression a little bit. And the first thing that I'm going to do to simplify this expression is I'm going to use the exponent properties to take this sum in the exponent and separate that as e to the kt separately times e to the power c. Now, we remember that when we introduced this notation c in the indefinite integral, that c just stood for some constant, right? Whatever constant you want. And if I take e and I raise it to some constant, then what results from that is just some other constant, right? And if I apply plus minus to that, again, what results is just some other constant. So what I'm going to do to simplify this expression is I'm just going to rewrite this entire quantity in the front as c. I'm just going to sort of recombine this expression to say the template and the format of all the solutions to this differential equation is p is equal to some constant times e to the power of some other constant times t. Now that I have solved the differential equation and I've simplified the result a little bit, we can use this equation to answer some questions about specific populations and make some predictions. So for example, someone says to me the initial population of a certain species, for example, was 300 members. So that means that the population at time 0 was 300. Someone says to me, one time unit later, t equals 1, now the population is 400. They say, based on this information, would you be able to predict the size of the population at time 3? And I think we can. Because if I plug this data into the solution template that we have set up previously, and if I plug t equals 0 into that expression, 300 must be what results. And if I simplify that, remembering that e to the power 0 is equal to 1, this tells me right away that this constant out in front of the function must be 300 units exactly. Likewise, if I plug in this data point that if t is 1, the population is 400, then I get 400 is equal to c e to the k times 1. And using the fact that c is equal to 300, which we found just a little while ago, I get 400 equals 300 e to the k, which implies that e to the k is equal to 4/3. From this, we can get the value that k is equal to, just by using a natural log to eliminate the exponential that is sort of keeping k trapped on the right-hand side of this equation. The value of k is going to be equal to natural log of 4/3. Now that I have found the value of all the unknowns in my equation for the population, the value of c was 300, the value of k was natural log of 4/3, I can now use this filled in equation to make any predictions I want to about what this population will do going into the future. For example, they asked me what's the population going to do when t is equal to 3? And so to answer that question, all I have to do is plug in 3 for the t value. So here is an example of a separable differential equation used in a physical context. If you have a population that is growing exponentially, then the differential equation that captures that behavior is separable. So you can solve that differential equation using the standard mathematical technique of separating the input variable and the output variable and integrating both sides. Once you've found the mathematical solution, which might contain a couple of unknown constants, You can plug in any specific data that you have about your specific situation, and you can use that data to help you to find the values of the unknown constants. And once you've filled in the blanks of all the unknown constants in your equation, then you have a lot of power and you can use that equation to do all kinds of things. For example, to make predictions about future behavior. For a final example, let's go back to the differential equation which showed up in the Season 6, Episode 1 problem set, which we did in class. We had an object there falling at high speeds with air resistance. If v is standing for the velocity of the object, then the derivative of velocity is equivalent to g minus some constant divided by the object's mass times velocity squared. If you express the differential equation for this object in this format in terms of the object's velocity, you end up with a separable differential equation. And to show that, let me give us a couple of specific values of g and m and k, and let us try to solve this differential equation. Here, if g is given by 9.8 units, I have a mass of 10 units and a k value that's equal to 2. I'll start by plugging those values into the equation. V prime is equal to 9.8 minus 2 for k, 10 for m, v squared. And if I, for example, multiply both sides of this equation by 5, then I get a 5v prime is equal to 49 minus v squared. Now, in this example, I do not have any instances of the input variable t for time. So I can separate this differential equation in the most extreme manner just by dividing the entire left-hand side, giving me 5 over 49 minus v squared. V prime is equal to 1 unit. And so I've completely separated the velocities from the times. And so I can integrate the function on the left side with respect to v and the function on the right side with respect to t. And we notice that this fraction here on the left is an exact match to the kind of situation that we learned about in the interlude when we were talking about partial fraction decomposition. If I want to integrate something that looks like this, I would start by factoring that denominator. Factor out a minus sign, and I'm left with a difference of squares. Now this denominator contains two different linear factors. So I can use the Heaviside cover-up method to help me to decompose this complicated fraction. And using the Heaviside cover-up method, if I plug in, for example, v equals 7 to the Heaviside, I get 5 in the numerator and then negative 14 in the denominator. And if I plug in v equals negative 7 to the Heaviside, then I get 5 in the numerator and looks like positive 14 in the denominator. And so partial fraction decomposition allows me to rewrite this complicated expression on the left as the sum of negative 5/14, 1 over v minus 7, and positive 5/14, 1 over v plus 7. And now I can calculate that integral on the left-hand side using just simple substitutions, giving me, in the end, negative 5 over 14 natural log, positive 5 over 14 natural log, is equal to t plus some unknown constant. Now, this equation is a little bit difficult to solve algebraically by hand. It is possible, it's just time consuming. If you take differential equations from me, I'm going to ask you to solve this equation manually. But since you guys are just here in Calc 2, I will let you off the hook. Okay, so what we have just said is that if you have an object which is falling and it is being acted upon by the force of gravity and the force of air resistance at high speeds, treat the gravitational constant as 9.8. If the mass of the object is 10, and if this constant k2 here has a value of 2, then the velocity of your object as a function of time follows this kind of shape. The velocity as a function of time is equal to 7 times some constant times this exponential, plus 7 in the back, all over c e to the 14 over 5t minus 1. This is the format of the velocity function for this falling object. Even though we don't quite have enough information about this object to find this final unknown constant in the expression c, we do have enough information here to answer one final question about the object's velocity. What happens to the object's velocity as time goes on and t approaches infinity? To see what happens to this expression as t approaches infinity, I'm going to start by rewriting the expression a little bit. I'm going to rewrite this fraction by dividing, essentially, both the numerator and the denominator by this exponential, which is going to change these terms in the front to just 7c, as this exponential cancels this exponential, and then in the back, 7e to the minus 14 over 5t. And in the denominator, similarly, this exponential will cancel with this one, giving me just c in the front, and then this exponential with the negative power in the back. Now, the reason why I did this, the reason why I rewrote this fraction using negative exponentials instead of positive exponentials, is because I know exactly what happens to an exponential when I raise it to a very large negative power. As t approaches infinity, and these exponents become very, very large negative numbers, the exponential term begins to vanish away and become 0. And so, as t approaches infinity and time goes on, all I'm left with are the two constant terms in the front, result 7 units. This quantity that we've just calculated, a velocity of 7 units, is what is called the terminal velocity of an object. For an object that falls with air resistance, eventually it stops accelerating. For an object at high speeds with air resistance, there reaches a point where its velocity and its speed maxes out and it doesn't speed up any further because the force due to gravity that's pulling the object downward is being completely counterbalanced by the force of air resistance that is pushing it back upward. And so the terminal velocity is what we have just found in this situation, the value that the velocity function has leveled off to as t has approached infinity in a limit. So I hope you have enjoyed the final episode of this class, where we set up and examined some separable differential equations arising from real-world situations.